Okay, let's dive right into this explainer, where we are going to act as investigators to uncover the hidden rules that govern literally everything that moves around us. I mean, we're surrounded by movement every single day, right? Cars driving, leaves blowing, balls flying through the air. But how often do we actually stop and think about the physical mechanics operating right under our noses? Well, today, we're going to demystify these physical laws and trace them all the way back to their scientific roots.
Let's start with a profound mystery. Have you ever just paused to wonder what exactly makes a resting object start moving in the first place? Or on the flip side, what forces a speeding object to suddenly stop? It's super easy to describe motion using position, velocity, and acceleration. We do that all the time, but just describing motion doesn't tell us why it happens. Does every single change in an object's position require a distinct cause? That is the core puzzle we are going to solve today.
Section 1. The invisible cause of motion.
To solve this, our investigation brings us to our very first prime suspect, an invisible culprit that we refer to in physics simply as a force. Now, a force isn't just a push that kicks a stationary soccer ball into the air, changing its speed and direction. It's actually a physical quantity that comes with both a magnitude, meaning its sheer strength, and a specific direction. And get this, it doesn't just affect motion. If you apply a force to, say, a lemon, you can entirely change its physical shape. Just squeeze it. So force is incredibly versatile, acting on objects in ways we can clearly observe, even if the force itself is totally invisible.
Now you might be wondering, how do we even measure this entity? The standard unit of force is called the Newton, represented by a capital N. In everyday life, the absolute smallest forces we can actually feel, like a super light touch on your skin, are in the range of millinewtons. But science has pushed the boundaries way beyond human perception. Today, in the year 2026, scientists in specialized experiments can measure forces all the way down to incredibly tiny octanewtons. That is 10 to the power of -24 newtons. It's an almost unimaginably delicate measurement of physical interaction, operating on a scale that honestly just boggles the mind.
Section 2. The Battle of Forces.
So we know what a force is and how to measure it. But what's really interesting is that in the real world, things get a little more complicated, mostly because forces are almost never working alone. They are constantly competing. Imagine two people pushing a stalled car together. You don't just look at one person's effort, you actually sum up the magnitudes of both of their pushes. Because they're applying force in the exact same direction, their individual forces combine to create a much larger total force, what we call the net force. And that net force is what ultimately drives the car forward.
But what happens when forces oppose each other? Think of a classic game of tug-of-war. When equal forces pull in exact opposite directions, the opposing magnitudes cancel each other out perfectly. In physics, we call this having balanced forces, meaning the net force is exactly zero. And the result? The rope doesn't budge an inch. There is absolutely no change in motion because the forces are completely deadlocked.
However, that conflict resolves the very moment one team pulls just a bit harder. By applying a larger magnitude of force, they break the balance, creating unbalanced forces. Suddenly, we have a non-zero net force. The result is instant. The rope finally begins to accelerate and move in the direction of the stronger pull.
Section 3. The hidden opponent. Friction.
Okay, so the crucial takeaway here is that a net force causes motion. But that introduces a massive plot twist. Why on earth does a sliding object eventually stop on its own, even when nobody is actively pushing against it? Well, whenever you push a box across a floor, you awaken a hidden opponent called friction. As you apply your push, friction immediately springs into action, applying a resisting force in the exact opposite direction. Sure, there are other forces at play too, like gravity pulling the box down and the floor pushing back up with a normal force, but those just cancel each other out vertically. It's the horizontal battle between your push and this invisible friction that truly dictates if the box moves.
Let's move to a fascinating little experiment to actually measure this invisible resistance across different surfaces. Picture a simple physical setup. We're using a stretched rubber band to launch a stack of coins and a spring balance to track things. First, we launch the coins across a wooden table and measure how far they slide before friction stops them. Then, we repeat the exact same launch on a laminated table. And finally, we do it one more time on a highly polished marble floor.
As we track the data from this, the results are super striking. We clearly see that the coins slide much further on the polished marble floor than they do on the rougher wooden table. Why? Because as the surfaces in contact change, the magnitude of the friction changes right along with it. A smoother surface applies a much weaker force of friction, which drains the coin's velocity far slower. This totally proves that friction depends entirely on the physical nature of the surfaces in contact.
Section 4. Newton's first law.
Which brings us to the grand climax of our explainer. What happens if we strip away the messy reality of the real world and imagine a perfectly smooth, idealized horizontal surface with absolutely zero friction? Way back in the 17th century, the legendary scientist Galileo used this exact thought experiment. He realized it was a total mistake to think objects naturally want to be at rest. He argued that if you remove all impediments like friction, an object moving on a smooth horizontal plane will simply continue moving indefinitely. He introduced this profound concept of an object's tendency to resist changes to its motion, which we call inertia. And decades later, in 1687, Sir Isaac Newton beautifully formalized Galileo's ideas into the foundational laws of physics.
That formalization is captured perfectly in Newton's first law of motion. It states, an object at rest remains at rest, and an object in motion continues to move with a constant velocity unless a net force acts upon the object. Now, constant velocity just means moving in a straight line without speeding up or slowing down. This law reveals the ultimate truth. A force isn't required to keep an object moving. A force is only required to change how it's moving. Without unbalanced forces, like our hidden opponent friction, things in motion would quite literally move forever.
So, to wrap up our investigation today, I want to leave you with a completely fascinating question to ponder. We just learned that objects in motion stay in motion unless acted upon by a force. So, how would your daily life change if the invisible force of friction suddenly vanished entirely from the world? Think about it. Walking, driving a car, or even just trying to pick up a glass of water. Our entire reality relies on this hidden opponent. Keep that in mind the very next time you slide a box or hit the brakes on your bike. Until next time, keep questioning the rules around you.